We will now discuss a variety of ways to prepare alcohols. Alcohols can be synthesized through substitution reactions like we've seen before. For example, if you have sodium hydroxide and a primary substrate with a leaving group, you can have an SN2 reaction, which will generate the alcohol. Alternatively, if you have a tertiary substrate, you could follow an SN1 pathway and generate an alcohol. Alcohols can also be synthesized via addition reactions. So if we have an alkene, we can use an acid-catalyzed hydration reaction to generate an alcohol. We could also perform an oxymercuration demercuration reaction to generate an alcohol, or a hydroboration oxidation reaction to generate an alcohol. Alcohols can also be synthesized via reduction reactions. As an example, if we take an alkene, we can subject it to catalytic hydrogenation conditions to generate the alkane. Similarly, we can take a carbonyl group, which is very similar to our alkene, reduce it using catalytic hydrogenation to generate our alcohol. To determine if a substrate has been oxidized or not, sometimes it's helpful to calculate the oxidation states. Basically, we're going to take a look at each of the atoms bonded to a specific carbon atom and then calculate the oxidation state. For example, this first reduction that we have above, this catalytic hydrogenation, we can calculate the oxidation states for this carbon atom to determine if it's been oxidized or reduced. So, if each hydrogen counts as +1 and a bond to carbon counts as 0, then the carbon here needs to have a net -2 oxidation state. Let's compare it to this carbon over here. Each of these hydrogens is +1. So this carbon atom has a net state of -3. Remember, reduction is a gain of electrons, and we went from -2 to -3, so we're gaining an electron. This is a reduction reaction. Let's apply this to our carbonyl reduction. So if we take a look at this central carbon here, we notice that the hydrogen is +1. Oxygen for each bond is -1, so this is -2. So the net between these two is going to be -1, which means our carbon atom has to be +1 to balance that out. If we take a look at the final form here, each of these hydrogens is +1. There's only one bond to oxygen now at a -1, so the total here is now +1 total, which means this central carbon had to go to -1. So we went from +1 to -1. We're gaining negative charge. This is a reduction. Many reducing agents act as sources of hydrides, so we don't need to rely solely on catalytic hydrogenation. We can also use something like sodium borohydride, where we have a negative charge on this species here, which means we can give up an H- to balance off that negative charge, or something like lithium aluminum hydride, also referred to as LaH. Again, we have the same state where we have the hydrogen here, which can be eliminated as a hydride. Hydride reagents are more selective than catalytic hydrogenation. So if we took a look at this species here, we have an alkene and a carbonyl group. Alkenes are reduced by catalytic hydrogenation, and so are carbonyl groups. So in this example, we would actually generate just the alcohol here. We would lose this alkene functionality. If we used a hydride reagent, we can actually have this react more selectively. So if we use LaH or sodium borohydride, these will only reduce carbonyl groups. So we'll generate the alcohol here while maintaining that alkene functionality. This phenomenon can be explained using the mechanism. So if we take a generic ketone as our substrate for a reduction and we add borohydride to it, we can first take a look at resonance forms. So this oxygen, because it's carbonyl, has a resonance form where the negative charge from that pi bond can go onto the oxygen atom, because oxygen is relatively electronegative. What that does is it generates this positive charge, which is an excellent electrophile. So in a reaction like this, when we lose the hydride, it will attack the carbonyl carbon, the electrophilic carbonyl carbon, and break the pi bond, moving the negative charge onto that oxygen. We now have an intermediate where we have a negative charge on that oxygen, and down here where the positive charge was, we have an hydrogen, though it's implicit and not drawn. After this, we can use an aqueous workup or an acidic workup. So if we add acid to this, the alkoxide here can pick up a proton and generate our final alcohol form. In the case of an alkene, if we tried to draw a similar resonance form, what we would actually see is we put a negative charge on a carbon. Carbon's not very electronegative, so this is relatively unstable. Because of that, this carbon atom here is not going to be very electrophilic, and we won't have a reaction with a hydride reagent. It's also important to note that lithium aluminum hydride is a stronger reducing agent than sodium borohydride. As an example, if we take this ester, where we replace the ketone with this extra methoxy group, there's no reaction with sodium borohydride. But if we use excess lithium aluminum hydride, we actually get a reaction where we lose the methoxide group and we reduce the carbonyl here. How does this work? Well, let's take a look at the sodium borohydride first. To explain why carbonyl groups are reactive to hydride reagents, remember we drew this resonance form. However, if we have an ester here, this lone pair of oxygen can also donate and form a new pi bond. When this occurs, we have the negative charge on the oxygen as before, but this carbon here is no longer as electrophilic. So if we add something like borohydride in here, this is not a great electrophilic site, just like the alkene example, and there's no reaction. But if we use lithium aluminum hydride instead, we will get a reaction, where this hydride will attack the carbonyl carbon and kick off these electrons to generate a new lone pair, to make this intermediate that we see here. This occurs because aluminum is our negative charge in this case. We put a negative charge on aluminum, which is a metal. Metals are generally very electropositive, so it's much more reactive because it wants to eliminate this negative charge on a metal. So this hydride will be lost much more easily from aluminum, which is a metal, than boron, which is not a metal, it's a metalloid. After this tetrahedral intermediate is formed, this lone pair can collapse back down to reform our pi bond and kick off this methoxy group. Even though methoxy is not a great leaving group, in this case, because these hydride reagents are actually bases too, we would generate methoxide in a basic solution, which is relatively stable. We have our aldehyde in this case. This is our one hydrogen that we've added. We can now use a second equivalent of lithium aluminum hydride to add in another hydride and convert our carbonyl into our final alcohol product. If we have a carboxylic acid instead of an ester, this type of methodology is also applicable. So in this case, we can either reduce an ester as we see here, or we could reduce the carboxylic acid. Either way, we will get the same final product if we use lithium aluminum hydride. To summarize, alcohols can be synthesized via substitution and addition reactions. Catalytic hydrogenation reactions can also reduce carbonyl groups to generate alcohols, but this will also reduce alkenes. We can use sodium borohydride or lithium aluminum hydride to selectively reduce carbonyl groups, and we can maintain our alkene functionality. And finally, lithium aluminum hydride is strong enough to actually reduce carboxylic acids or esters to alcohols. Sodium borohydride is not strong enough to perform these reductions.